To examine potential and kinetic energy changes, we have to choose matter that is much easier to work with than the molten iron that you just saw. Stephanie and Carmen, how are you going to go about doing this?
Well, we set up a computer interface to graph the energy changes in water.
Okay, good choice, since water is a very common example of matter and it's easy to work with in the lab.
Well, we're using the computer to connect the computer world and the science world. You know, since scientists use computers all the time to store and analyze all their data.
Good. Okay, so now how is your computer working today?
Well, we've done quite a few trials, but at first we had a bit of trouble getting our probe to register. But after checking the connections, we got it working quite well now.
Good. And what's your probe able to measure?
Our probe is measuring the temperature change and the ice melting.
Okay, and what does your computer do with these measurements?
Well, our computer records and graphs data.
Okay, let's take a look at your temperature time graphs a bit more closely.
Well, the first rise is the ice warming to its melting point. Then the first plateau is the ice going from a solid to a liquid, and the solid ice is actually melting.
Okay, now I see some fluctuations in your graph during the melting. What is happening there?
Well, the probe was frozen into the ice, and as the ice melted, the probe broke loose, and it bounced around and sometimes hit the bottom of the beaker. So.
Okay, and then I see now the graph straightened out a little bit more, so you must have collected your ice closer to the probe. Good. Okay, now what happens here as the graph rises?
Well, right here is the second temperature change with liquid water, and then up at the top, the plateau, that is the phase change where liquid water is changing to water vapor.
Okay, so now why aren't you able to show a further rise in the graph as you heated the water vapor?
Well, water vaporizes and goes into the atmosphere, and the probe can only, tell the temperature of the substances inside the beaker and not read anything outside. So.
Good. All right. So let's examine these changes a bit more closely on the paper over there.
Okay.
The most useful way of describing the relationship between two quantities is by drawing a graph. This can be done by hand using graph paper, but today it's common practice to plot experimental data on computer-generated graphs. Computer technology allows us to do this with incredible speed and precision.
This graph looks like the graph the computer made.
That's right. In what way are they the same?
Well, on the horizontal axis, the time in which the heat was added is there, and then on the vertical axis we have the water temperature. So as the thermal energy is increased, the water temperature increased.
Good. Okay, here we have the ice remaining in its same physical state, solid. Okay, at 0 degrees Celsius we have added heat energy that causes the ice to melt.
So it's solid to a liquid, and it's melting.
That's right. And melting is an example of a phase change. A phase change is a change in the physical state of matter. Okay, what do you notice about the temperature during a phase change?
It's constant.
That's right. So the temperature does not change during a phase change. Here we have then the liquid increases in temperature.
Okay.
Now at this point here, what happens at 100 degrees Celsius?
It goes from a liquid to a gas, and that's
because
boiling.
It's boiling.
That's right.
The temperature is 100 degrees Celsius.
Okay, and this is another phase change. What do you notice about the temperature change during this phase change?
It also remains constant.
That's right. Now, in your lab, we have the water boiling away over there, but we're unable to measure the temperature change. What would you predict happens at this point?
Well, the temperature would probably increase again.
It would increase, and the temperature of the gas would just go up.
That's right.
And this would be of the gas.
Okay. Now, in your lab, was the temperature for the water boiling at 100 degrees Celsius?
No, it was 99 degrees Celsius because the elevation. And the water boils when the volume vapor pressure is equal to the atmospheric pressure. And
because we're at a higher elevation.
Yeah, the elevation, there's lower pressure at a higher elevation, which causes the boiling point to lower.
And was at 99 degrees?
Yeah.
Okay, now we're not climbing any mountains. Will the temperature, if we did this lab tomorrow, be the same?
Well, it probably wouldn't be the same because weather can affect the local atmospheric pressure.
That's right. So just like all things in our lives, it always depends on weather.
Did you know that at the top of this mountain, water will boil at 86 degrees Celsius, slower than the normal boiling point? So if you want to hard boil an egg, you'll need more than the normal 10 minutes. It will take about 30 minutes to cook the egg.
The effective pressure on boiling point also explains why pressure cookers save time in the kitchen. A pressure cooker is a sealed container which allows steam to escape only when it exceeds a certain pressure. The pressure above the water in the cooker is the sum of the atmospheric pressure and the pressure of the steam. Because of this increased pressure, the water in the cooker will boil above 100 degrees Celsius, and the food in it will be hotter and cook faster.
Okay, so physical substances can change their physical state of matter from solid to liquid, liquid to gas. But there are some exceptions, and you'll soon see why.
Okay.
When iodine is heated, the crystal changes from a solid to a gas without passing through the liquid state. This is called sublimation. Sublimation is the process they use to make freeze-dried food like this. This food is put in a chamber where the pressure is below the vapor pressure of ice. This causes the ice crystals to sublime. So when you're ready to eat, all you have to do is just add water. Freeze-dried flowers are another product of sublimation.
This is where the process starts. With fresh flowers, we bring these flowers in especially for freeze-drying. We give them some time to open up. Once they're full bloom, then we snip the blooms off of the stems. We place these blooms on trays. The trays are full. They're slid into the freeze dryer. The freeze dryer has been prepared at minus 45 degree temperatures. So the flowers are frozen very quickly. Once they're fully frozen, we give them about 12 hours. Then we start the vacuum pump up. Under vacuum pressure, sublimation takes place. That's where the ice crystals in the flowers transfer from ice to gas, missing the water stage. Gas, moisture in the chamber migrates to the lower chamber, which is at minus 65 degree temperatures, and reforms as ice. Then we can isolate the two chambers and defrost the lower chamber, and that's how we remove moisture out of the machine and away from the flowers. This is the same flower air dried, and you can see that there's been a lot of shrinkage, discoloring, browning. These flowers will last for years.
Now, back to the iodine. When the gas cools, solid crystals form without passing through the liquid state. This is called deposition.
We've already examined the temperature time graph for the heating of water. Carmen, what does a graph look like for the reverse process, cooling?
The curve is reversed.
That's right. Have a look.
Can the temperature time graph be used for other pure substances besides water?
Yes, but specific heat capacities, melting and boiling points, differ for each substance. So the shape of the graph varies for different substances. Let's have a look at a temperature time graph for iron. In this foundry, iron is heated to its melting point, undergoes a phase change, and is heated further. The molten iron is then poured into molds, it cools, solidifies, and then cools to room temperature.
What is the process in which iron is molded?
First of all, we have to take an object, and then we make an imprint of the object's bottom and the top. Once we have that imprint in sand, then we can take those two pieces and put them together. You can see this line here. These are the two pieces that have been put together. And so putting those two pieces together gives us the object when we pour the metal into it.
So is this a special kind of sand?
This sand is a special type. It's a very fine sand from the United States, and we put hardeners into it, so it's very hard as well.
Oh, I see. So what is this for?
Okay. Gases build up in the mold as the iron cools, and those gases could ignite all at once, moving the mold about. So we use gravity with these weights to keep that mold down, just for those little tiny explosions like inside. And it keeps the mold stable.
I see. So what are these holes for?
Okay. The metal is poured right here and goes down inside here and then rises right in here. You can see how deep that is. That's about, about a foot and a half deep or so. And that's where the object itself is formed.
You pour the metal in here and then it forms.
And it comes out there and we can see it. And that lets more of those gases come out.
What is the purpose of the little flames?
Okay. We also light vents around the mold just to make sure those gases burn off orderly. And that enhances the stability.